as you can see, okay, so in this talk, I'm going to introduce first my research context, covering the notion of user-centered human-machine systems, and also the research background about active recognition and behavior analysis in smart healthcare. So follow that, I will introduce a hybrid approach to computational behavior analysis, and then will outline a number of computational behavior analysis related research activities and projects. And finally, I will probably discuss future research directions and summarize, potential areas. So first, probably let's take a look at the traditional human-machine system. So which is normally referred to closely integrated human and system, machine systems, which actually are quite common in our daily life. As you can see from the left-hand side, these pictures, which include human operators operating a crane, a car, fly a plane, or using simply a mobile phone or medical devices. Yeah. So as you can see in the right-hand side, the abstract conceptual depiction depict these traditional human-machine systems, and in this context, the role human played is mainly as an operator or controller. The human operator observe the effect or consequences of the machines and also to the environment, and that exercise control to the machines. However, this has been changed, yeah, with the emergence and development and large-scale uptake of the pervasive computing, Internet of Things, mobile and distributed computing. As you can see in the right-hand pictures or diagram, so the role people played has changed. It's not only as an operator, but more as an entity to be served, for either the user experience, satisfaction and well-beings. You can see it's the machine observe and serve the users, and the machine observe the behavior and how the user react to the services, and then take a control. So that is what we are now talking about. Anywhere, anytime computing, context awareness, personalized or adaptive or anticipatory, services. So such application scenarios, as you can see, include applications in smart home, smart cities, and many intelligent transport or smart energy. Some probably examples you may not be aware, even say in our daily life, like you wear a smart watch, Fitbit, you use smart speakers and all type of online recommender systems. Yeah. So we think this is we refer to this as a notion of user-centered human-machine systems. And this notion can be probably best characterized and depicted in these three word views, as you can see here. So I think from this, you can see, probably observe three main characteristics of the change. Yeah. One is in growing separation of the physical world, sensors, actuators, smart objects, from the cyber world, the web, the cloud, the edge. So the computing capabilities is more, not to say they are all embedded, integrated in one machine. Yeah, this is one. The second, you might notice the change or the evolution of the interaction and the communication, yeah, between these three entities. So it's not only human, physical operating these devices. You can use gestures, you can use voice, all different type, multimodal interaction technologies. And the most important, I would say, probably you notice the human now in this picture or in this context now become the first class citizen. It's not to say just an operating machine, but actually it's a part of the whole system. Yeah. So as a result, user and user behavior and interactions require explicit and formal representation with this new, probably I would say, type of say user-centered human machine system. Yeah. And this new will bring a whole raft of new research questions, issues, and challenges. So as you can see here, say so how human machine systems better serve the users, how user and the system interact, impact each other, and who are on control. Yeah. And clearly there are issues. You want to a machine or service or probably more posh word, you can say use app or services. You know, I think the key is how can they understand what a human is doing or they are thinking. So that brings up research issues about computational behavior analysis, user and system modeling, and interaction modeling and system dynamic. Yeah. The challenge, probably you can see, among the three words, is not static. Each word itself actually is evolved. Technology is going, hardware, software, humans understanding also changing. You need, you want, you for a particular application also it's changing. So on top of that, for different application, the human behavior is different. So this brings a whole new challenges to this research. In this backdrop, I and my team probably in the past decade have been working on assistive living and smart healthcare in smart home. Yeah, so probably this is the best application scenario for the user-centered human-machine system. So the idea in the smart healthcare within a smart home is to deploy, ICT technologies like Internet of Things, sensors, and data analytics systems. So to monitor what an inhabitant is doing in that environment. And that could be the physical activities or vital signs of healthcare, yeah, or the physiological parameters. By analyzing them, therefore, the system can provide support for either like independent living for people with mental impairment, or support, self-care, self-management for people with chronic disease. And also more and more, we are care about the well-beings, like early risk detection about mental health, depressions, anxieties, stress. So it's cover all different aspects. So in this context, our focus on activity recognition and behavior analysis, because we know only when the system can figure out what is inhabitant is doing or how his or her behavior change, then they can provide best services or support. Yeah. So in this context, when we say activity, we refer normally we will say activity of daily living. As you see, they are basic ADLs like making meal, making drink, dressing up and down, hygienes. And there is another type of core activities we call instrumental ADL. That is refer to the use of technologies, housework, take medication, financial, your own financial management. Yeah, no matter what type of activity. So there we need to distinguish from activity recognition from behavior analysis, because they are has subtle differences. Yeah. For activity recognition, the purpose is to decide what an inhabitant is doing. Yeah. And this is very useful for supporting independent living, or contexts where we see timely support or assistance. Behavior analysis is different. It's aimed to decide how activity is performed, yeah, by a particular or specific users, and to detect the patterns a particular ADL is performed over a long period of time. The logic behind that, as you may be aware, lifestyle is becoming increasingly important in healthcare. So by monitoring the behavior change, it could provide key markers for the change of your health or well-being. If you have some medical conditions, that may also indicate it, it's become better or worse of the situation. So there are different level of research and also serve a different purpose. Before we discuss our research, probably just clarify a little bit of some background. Yeah. So activity of daily living, there are many different ways they can be performed. As you see here, there is a single inhabitant, sequential activity of daily living. Basically means, inhabitant or a person perform one activity only when he or she finishes that, and then he will do the next. And there is also a scenario, single inhabitant, but he or she perform interleaved, parallel, or concurrent activities. And then there are more complex scenarios like multi-inhabitant, and they joint perform sequential activities, or each of them perform independent activities, or they collaborate with each other, jointly perform multiple activities. Yeah, so you can see it's just reflect the different temporal or spatial constraint in this process. Yeah. The second, probably just a highlight here, our research is mainly focused on single user. Yeah, but it could be a sequential, or it is we also address interleaved, parallel, or concurrent activity recognitions. And another background I would like to mention here is there are different ways you can monitor, yeah, the activities. So there are vision-based monitoring, use cameras, and then there is a wearable sensor, using wearable sensor, attached sensor to the human bodies, measure directly either medical vital signs or other kinetics, signals. Therefore, you can infer activities. It is normally used for monitoring exercise, like walking, running, or sitting up and down. Yeah. Another is non-region based monitoring. Basically, we apply ambient sensors and deploy them in the environment. Yeah. So therefore, they can monitor the movement or the change, location or the object the user or inhabitant interact with. And through the interactions, then they try to infer the activities. So this is a different ways. And our research mainly focuses on using both wearable sensors and ambient sensors. So that's just give you a little bit of background of our research. So with this background, I think the research question for in our research is given a real-time data stream from multiple sensors in multiple form, how to infer the activities being performed. So you see this data series from multiple sensors. So probably we humans, when you look at somebody, go to kitchens, pick up a kettle and get a cup and take out a teapot, you can infer, oh, that person is going to make a cup of tea. Yeah. And if you see he open the oven, take a tray, you could guess, oh, he might want to do cooking. But the machine don't have this knowledge. Yeah. So to do this, the first step naturally we say we need to model this knowledge and tell the machine that is the what activities. So modeling activity of daily living is probably first step, providing computational models. Yeah. The second is machine, you need to give, we humans have the cognitive capabilities. We can infer, we can do reasoning, based on multi-source informations, we can infer so what the situation is or what will happen. The same, we need to give the machines of these reasoning capabilities so that they can, based on the received observation or sensor data and then do the inference, yeah, to derive what activity a user is performing. And then, the behavior analysis basically focuses on long term. So we recognize what a user is doing today, or we recognize what he or she is doing next time or next week. And over a period of time, we can observe, oh, did he or she change the way he perform the activities? Surely, it will, just like you undertake any task. When you become familiarized, you will do it more quickly. Yeah. But still, to some stage, it will be stabilized. Yeah. But what is the final stabilized way you do something? That is what we want to know. Yeah. So just a quick introduction about the background. There are different ways for activity recognition. Basically, there is one is based on data mining and machine learning. Yeah. So this is probably the main approach. Yeah. And this approach, there are two main type of method. One is called generative modeling and recognition, like hidden Markov, dynamic Bayes network, and POM-DP. And another is discriminative modeling and recognition, like nearest neighborhood and support vector machine and decision tree. Yeah. But no matter they have a different method. The generic methodology for data-driven activity recognition is more or less the same. Basically, you create the probabilistic or statistical active models, and then you learn the active models. Basically, you train the parameters, yeah, and then you use the active model as a classifier, yeah, for activity recognition. More or less, this is the way, high-level generic methodologies. The advantage is the method, for data-driven is able to handle uncertainty and temporal information, but also it suffers the cold start problem because it requires large scale pre-existing data set. There's also other problems you see, because when you learn the data model, only when the data contain what is happening. Yeah, if the data set does not contain the information, the knowledge, you will never learn that. Yeah, that's one. Another is you learn something from one particular user's data, but we all do things differently. So the model you learn from user A may not be suitable for user C or user D. Yeah, so that is a problem for data-driven activity recognitions. And there's another approach we called knowledge-driven activity recognition. It is based on knowledge engineering and AI techniques. Yeah. So again, there are different ways. Yeah, different ways. So, but the generic methodology still we can summarize more or less. Yeah. So in this approach, we acquire domain knowledge and heuristic about activities. And we specify activity model directly use knowledge representation formalism. Yeah. And then we develop reasoning mechanism and or reasoning engines. So in this case, performing activity recognition is more or less through formal logical reasoning. Yeah. Of course, because we have a different knowledge representation formalism. Yeah, we can use first order logic. We can use action event theories. We can use description logic. Each different knowledge representation formalism has corresponding, the way how do you model knowledge entities, how do you do representation and reasoning. Therefore, it will leading to different implementations. But that is implementation details. But the high level principle and the methodology, I would say more or less is the same. Yeah. For this approach, there is advantage. There is no cold start problems. Yeah, we all know, for example, how do you make a cup of tea? We all know how to prepare a pasta. Yeah, why do we ask a machine to learn it? We know how to do that. Yeah, why do especially in the healthcare domain, it's very difficult to collect large scale data set. Yeah, another probably advantage for knowledge-driven approach because it's based on logical inference. It's semantically clear. Yeah, in terms of modeling and in terms of the conclusion you draw from the logical reasoning. That is you think about the tractabilities and soundness of not traditional knowledge-based systems. But of course, they have they suffer from a disadvantage. People will complain, how can you generate all active models? It's static, it's rigid, it's how do you handle uncertainty? That's all different problems. So we try to marry the advantage or strengths of the two approach, and meanwhile, to mitigate the disadvantage. So in this case, we propose a hybrid systematic approach to computational behavior analysis. So comparing to either data-driven or knowledge-driven approach, within our approach, the modeling is not a one-off activity, but an iterative multi-phase process. And the modeling, recognition, and the behavior analysis are interweaved, yeah, both conduct and improved incrementally. So the approach can be depicted in this way. Suppose we have a smart environment, with a human inhabitant living in this environment. We first apply a knowledge-driven approach, carry out knowledge engineering. We can build activity models. We know we cannot cover all activities. Therefore, we do not expect the active model is complete. Yeah, but it doesn't matter. We know it's incomplete. Therefore, we call it seed active models. But we will learn the models and to incrementally, increase that. Yeah. So that is the first stage. Second stage, once we have the seed active models, then we can use discipline logic, reasoning inference to recognize the activities based on the sensor observations. Again, because we know the model is not complete, therefore we do expect the activity recognition result will be, contain two types. One is recognized activities. Yeah, we call it labeled activity traces. Another is unlabeled activity traces. Basically, so because that activity has not been modeled, the machine does not know that. Therefore, the machine cannot recognize that. We admit that, no problem. We collect these two sets of data. Yeah. And it's in the third phase, we apply machine learning techniques is here. So at this stage, we will apply the machine learning to learn the new activities. Yeah, it's a pair the user performed, but it was not in the seed active models. We also will to learn how, suppose, activities are recognized in a labeled activity traces. We can learn how a particular user perform that activities. Yeah, so that is similar. We learn the user's profile. And again, if we do the long-term data analysis, this phase, we can also analyze how a user perform a particular activities over a period of time. That is the user's behavior. Yeah, that is changed, from 3 months ago or half a year ago, etc. Yeah. Once we learn this, then in the fourth phase, we can update the activity models. Yeah, and also increase the user profile. And this process will iterate, yeah, until there's no more new activities can be captured and the new user profile are fully established. Yeah. So if we look at this framework, so the first two phases is basically knowledge driven. Yeah, it's focused on activity recognitions. And the second and the third phase is data driven. It tries to improve the model and also to derive the behavior. So this is a framework we have been working in the probably past 10 years. So you may notice there are some papers in the slides. Basically, that's the work we published. So in the past decade, more or less, for each of these process, different technology component, we have carried out corresponding research. So I will quickly go through this, all different type of research. So the first, probably very quickly, we will create seed activity models. Yeah. So we conducted conceptual context modeling. Yeah. So activities happen in temporal spatial dimensions related with various contextual information. Sensors, objects, items. Your cup, teapot, kettle. That is the object you use. Yeah. And in different locations, in kitchen, or if you have a hygiene, you may happen in bathroom. Yeah, so there are also temporal informations. You do something in the morning, you do something in the evening or midday. So they are all interlinked. So we create a conceptual context model, the first, and then we conduct conceptual activity model. No matter if you think about what active daily living, they always link to different location, object, timing. Yeah. So how to perform that? What are involved? Yeah. So that we explicitly specify the relationship between object and activities and build a hierarchical structure to encode the relationship between the activities and the object, also including the activities. Yeah. And then we create a computational activity and context modeling. That is where we generate the first seed activity models. Again, in this case, we use ontological engineering. Yeah, I'm not sure you know, we use a Portage tool framework to encode all this. And therefore, we generate activity concept class. Yeah, that is a generic activity models, but we can also generate instances of each classes for a particular user. And that is a particular way a user perform a particular activities. So that represent the profile of that user. Yeah. So that both them are fed into the system for activity recognition. It's the phase 2. Yeah. So when we come to the phase 2, we perform activity recognition. I think here you can see we need to first segment different sensors. Yeah. So we analyze the different characteristic, of the streaming data series. They are, you see here, there are different scenarios, fixed size, no overlap, or dynamic sizing, no overlap. And then you see dynamic sizing with overlap. And then there is a sliding window, which can shrinking, which can expanding to adapt to the, the data streaming in, as data streaming in. Yeah. And on top of that, we develop a non-tuple time window models, and then we develop an algorithm. This is just this is published in a separate papers, but I just give you that is what we did for sensor data segmentation. Once we have the segmented data, so when we have the active models, and we capture the contextual data, and we model the activity on ontology. In that case, activity recognition is equivalent to concept classification, or more using the discrete logic term, is like sub-assumption reasoning. Yeah. So if you look at this, you see this is activity classes, and this is the properties, and this is the range of types. And when you interact with the object, and the sensor attached to the object will fire, and then it will map to the different properties of the activity class. Yeah, and then you use the semantic reasoning, and it can derive, which class that activity description will be corresponding to. So that is the way we apply subassumption reasoning to perform activity recognitions. And our approach will work in real time, perform continuous progressive activity recognitions. So as you can see here, as an activity unfold in a timeline, new sensor data come in and it will be dynamically segmented into different chunks. Yeah, and within each chunk, the data will be mapped to the properties of our activity model, like ontological concept, and they form a activity description. And then we here perform subassumption reasoning. Then we can recognize, as I mentioned, it could be a recognized activities, it could be a non-recognized activity if the model has not been covered. And this process can be repeated. Yeah. So therefore, it can support continuous progressive activity recognitions. So this is the second phase. And then once we do this, it's move to the third phase. Yeah. And as you can see from the last slides, from the second phase, it will generate two data sets. One is unlabeled activity traces, and basically activity which happened but which has not been modeled, therefore they cannot be recognized. And the second is labeled activity traces, which recognize activities. Now it's the third phase. We will apply data mining machine learning techniques to learn. Yeah, for example, you can see here, the first, we want to learn from unlabeled activity traces to learn the new activities. Yeah, here you can see from the diagram, there are different. Yeah, so there is a subset data set of unlabeled activity traces. We will define semantic similarity metrics between unlabeled activity traces, and we compute similarity between all those unlabeled activity traces, and then classify those activity traces into subset. Basically, each subset corresponding to new activities, but does not mean that activity is a regular activity. Then we will calculate the frequency of the activity occurrence, and then we will decide, based on threshold values, whether or not this is a new activity. Based on that, we will expand the models to improve the completeness of the active models. Yeah. So this is an algorithm. Yeah. Again, for the labeled activity traces, basically for those recognized activities, you see here again, they are in a data set, and then they are partitioned to sub data set. Yeah. And we will define again similarity metrics between different labeled activity traces. We basically transform a vector of object signatures, because when you capture is basically object the user used, map to the sensor. So we construct a vector of object signatures, and then we use Pearson similarity algorithm to calculate that. We compute the similarity, and we then classify the activity traces into subset. Yeah, basically each subset corresponding to unique patterns a user perform particular activities. Yeah, again, after we calculate the frequencies of occurrence, we can decide whether or not this is a pattern. or is a unique way, or simply say if it just happened once, it's just a random occurrence. But if it happen every all the 80% of the activity occurrence, then that's maybe the pattern. The user normally do things in this way. Yeah, that's form part of the user's profile. So this is basically acquire the profiles, yeah, to improve the model quality. So that will support when we talk about personalized services. What we mean personalized, because we base on that person's specific way of doing things. Yeah. So after the two, and then once we can identify, recognize activities, then over a period of time, we can learn how the user perform activities. Yeah. So that will involve calculate the frequency of occurrence of activities, yeah, to decide if activity is a regular activity. And then if it is a regular activities, again, does it have active patterns, a unique way it is performed? So probably I'll not go to details here, just described in particular in a smart home context. How do we participate a day into different time slot? And then we monitor the starting and timing of activities, and then we do the analysis and extract the patterns. Yeah. So roughly that's the third phase. So we, as you can see, we combine modeling is a first phase, and recognition second phase, and behavior analysis and model perfection in the third phase. And in the fourth phase, basically we will decide, to enhance the active models. Yeah. So to decide where the learned activity will be added in the ADL ontology or models, and decide the labels, name, the learned activity. But in both cases, human validation is needed for quality control. Yeah. And again, we will create user active profiles based on, the result from the learning the labeled activity traces. Yeah. So learn the unique way or patterns a user do something. So I will not go to detail. So we have some, we implement a prototype system, as you can see here. I have demos. Next slides probably just. So this is a smart lab. We have conducted various research, and here probably is let's see, a demo show you experiment of activity recognitions. So I'm not sure whether or not here you can hear the sound, but sound does not matter. Mainly probably you can see all those sensors are attached, simulate to attached to different object. And when a student touch one sensor, it simulate, the user interact with the object. So that is, as you can see, how the system, will do the collect all the data, mapping to the ontological entities, and perform the inference, and from which, it's derived the different type of activities. Yeah. Okay. Just to give you a taste, I will not stop here. Just beware of the time. Yeah. So we do the testing evaluation. So so that is the probably you can see we list a number of papers. That is the result which support that these papers. Just give ideas. So And now probably I introduce the systematic hybrid approach. Now I'm going to quickly go through a number of activities surrounding behavior analysis. Yeah. So the first, probably each slide may be a research publication. So I will not be able to go to detail, just to give you a rough idea. What's the purpose? What's the aim? What to do? What have we done? So this probably is mainly focused on complex active recognition. Progress, what we talk about is mainly focused on single user sequential active recognitions. So this one we focus on active recognition, for interleaved, concurrent, and parallel activities, which we use combining the distribution logic with temporal logic. And as you can see here, we extended the original active model with temporal inference. Yeah. And then because it's parallel or concurrent, that involve multiple activities. So the K is a temporal relationship between different thread of activities. So again, you see here we use ontology to characterize the different sensor data activities and create inference rules. And we implemented this in a multiple agent system. So there are a single activity recognition agent looking on individual thread of activity, sensor series, streaming data, and how a collaborative activity recognition agent will coordinate different thread of primitive activities based on single active recognition agent. So that is the way we did that. Another, again, we expanded the research. Here we focus on fine-grained activity recognition using fuzzy logic. This is to try to address the coarse-grained activity recognition drawback. Because when in progress, we say the active recognition is based on user and object interaction. So the assumption is you attach a sensor to an object. Once the sensor fire, we assume the object is used. Yeah, that is what. But for some, there's no evidence to confirm that is the case. Yeah. So, for example, you want to pour some hot water into a cup to prepare the tea or coffee. How do you know the water is in? Yeah. So in this research, we combine description logic with fuzzy logic to model imprecise data. Yeah. We then apply multi-model sensing for single object. So you see here, this might see, this is some prototype built up in our lab, for each single object, could be a cup, a kettle. We attach 3 sensors, yeah, to measure, for example, the temperature, the level of liquid, or the angle of you pouring water. So this show you the I think the interface of the portage. We use the I think fuzzy logic, fuzzy DL plug-in to the portage to specify these rules and then develop a inference algorithm. Here, probably give you a more clear examples. Say we want to detect fine-grained pouring actions with a kettle. So you see here we attach 3 sensors. One is liquid, one is temperature, one is gyroscope sensors to this. And then with the data coming in, it will segment it. And for each segmented data set, you see its top, will collect 3 sensor data. Yeah, one is about liquid level, another is object temperature, another is gyroscope will represent the angle, the pouring. So for them, we first do the falsification, basically attach and map them to the values, and then there is a fuzzy rules which will do the inference, and when the rule is met, then you can recognize the activities. So
Luke, would you be able to summarize in a couple of minutes time?
Yes, okay, I can. Yeah. So
appreciate that. Thank you.
Yeah, no problem. We have 5 minutes. Yeah, okay. 5 minutes is okay, Sajal?
Okay.
Okay. Yeah, okay. So probably another study surrounding the behavior analysis is about sleep behavior analysis. Here you can see one is we perform sleep position recognitions. We deploy sensors in different parts of human bodies. And then we use active graph. We try to analyze sleep-wake stage analysis. That is one. And here we try, based on sleep behavior, to derive the potential disease, try to correlate sleep quality with the disease. Here we focus on, we have a data set from, I think, US National Sleep Research Resources. So we correlate the sleep quality with, diabetes, hypertension, kidney disease, and sleep apnea. Yeah. We also, my team also carried some research on actually learning behavior monitoring using EEG and eye trackers. We try to, in this specific study, we try to identify, if our learner, what is the learning style? Does he prefer visual information content, or does she or him prefer verbal? So that is eye tracker and EEG data, and this is what we process. We use principal component analysis to process the EEG data, and then we apply. We use the estimate, the box plot from the different channels of EEG to extract features and apply the SVM classification method. Yeah. We have also a number of projects on this sphere about computational analysis. One is mobile muscular skill user self-management. So probably I will not go to details. Basically, if you suffer from arthritis and you can do self-management, monitor at home, use the wearable sensors, and they collect data and then analyze data. So that is a collaboration with Norwegian Research Council. Another project is also about the activity recognitions. So that is, you can see patient-centric models for remote management, treatment, and rehabilitation for autistic children. So basically, we want to move the assessment and the therapy of autism children from clinic environment to home environment. So here you can see we use videos and cameras to monitor the when the children give a video, a game to play, we monitor the brain activities, and then we will analyze that. And the key feature here you may see is provide 3 different interfaces for family members, therapists, and clinicians. Yeah. The final one is probably is an ongoing one. We try to apply the behavior analysis to the cybersecurity context. So as you can see here, we want to go through multiple alert in a network. we want to perform data mining to establish the situations, basically from alert of multiple intrusions, but many of them are false. Yeah, and then how to reconstruct the attack scenario. Then from the situation to establish the responses. So that both tasks are addressed in data and knowledge hybrid approach. So I think roughly that's what we have been working on computational behavior analysis. So just a quick summary. So we think CBA is key to smart user-centered human-machine systems. Our focus is on probably smart healthcare, but I would say it's useful for more broader applications. Yeah, so-called smart applications in smart cities like that. And the hybrid approach is promising, but I think it's still at an early stage. And most importantly, that when you recognize activity, that is only first step. It's not the whole story. So what when you recognize activities or the behavior change? Yeah, I would think our future work probably partially focus on unobtrusive long-term behavior monitoring and freestyle activity recognitions, and probably multi-behavior data fusions and analysis method. Yeah. Probably another is how can we combine knowledge-driven with data-driven to provide semantics for later stage. We talk about decision interpretability or explainability. So that is what we our focus at the moment. So thank you for you listening. So Sajal, I think sorry about 2 minutes.
Thank you. Let's thank Professor Ling Liu Chen for a wonderful talk. A multitude of different things, application of sensors, IoT, and data collection monitoring in a smart health context, and how to even inject the behavioral monitoring into the solution process. So very much socio-technical research, which is very important in today's world of technology. So it's time for questions now. And Lining, I'm sorry that your captions I could not, and looks like it is from your end, because when I speak, nothing shows up. So something you can figure out later. But I tried, I could not figure out. But anyway, so let's have some time for question answers, Q&A. Anyone who has question, please ask. Yeah, Ardhendu, you have some question?
Yeah, thank you, Professor Chen, for the nice talk. I'm not very familiar with this, but I'm interested in smart health applications and how we could sort of use the wearable sensors and other kinds of sensors to that. And I guess part of your talk here is saying that you have some knowledge-based activity models, and then you refine them on a per user basis based on the traces that are then collected, right? Yeah. I wonder about the scalability of the approach, though. Is it not true that you would need a new model for every person? And secondly, like in smart health applications, is it really critical to know that whether somebody is making tea? I'm not aware of the particular use case scenario of your case, but just your thoughts on it.
Yeah. So for the first question, so I think your question is about scalabilities. Actually, we propose the iterative process exactly want to address the scalability problems. So as I said, we know we cannot cover all permutations, of different ways of perform activity. Even just one person, so many activities you cannot predict. So that's the way we say we produce initially based on knowledge and ontological engineering. We can, or from prior domain knowledge, we build a seed activity models. And then later stage, once we collect the, basically like, just like a data-driven approach, you base from the pre-existing data set. And in our cases, we already probably have a good start. We have some seed incomplete active models for you to play with. You still generate the data set, but with this seed active models, we are able to separate you. Therefore, on top of that, we do further processing. So yes, that's the way we will address this problem, and we believe we can achieve that for this. Sorry, I did not get the point of your second question.
Yeah, no, sorry. That was like, it was just
comment.
Activity recognition. I understand the question, but I was wondering, in case of a health scenario, like, is it critical to understand, for example, whether somebody's making tea or whether they are just cooking?
Oh, okay, I see. Understand. No, in healthcare, what we talk, the digital health, there are many different use scenarios. One, what we talk about, independent living. You can think about people with Alzheimer or dementia. The biggest problem for them is in the study room, I'm thinking to prepare a cup of tea. When I go to the kitchen, I forgot what I'm come here to do. When they prepare, they say, I want to prepare a meal, no matter lunch, dinner. They may open the cook, they put some tray, but they forgot, oh, what I'm going to do next. This is a scenario, say, like prepare, even make a cup of tea, make a cup of coffee for those people. It's difficult because for people with Alzheimer and dementia, the big problem is the loss of memory. They lost track what they want to do. So that is one scenario. We want to monitor and then provide context-aware or timely assistance. So if we know, if you think about a team in a personalization, monitor the elderly, 78 or 85 years old, they do something, or they say, oh, you get you boiling water, you take a cup, you take a teapot, but you seems get nowhere. That system can remind him. So that is a scenario, yeah. And the other scenario is like, say, there are different usage. Like I mentioned, the arthritis case is, say, a patient, for example, suffering from arthritis. The case is they have already been diagnosed and become stable, but they become home. They need to rehabilitate at home. Normally, they need to, every week, they need to go back clinics to talk to the clinicians to report back. But with this IoT or sensor, at home, they can manage all those parameters. System will record that, and the data will be relayed to the clinician. So that's the way is they reduce the number of visits for the patient to the hospital, and also provide a more timely monitoring and suggestion. It's not, you do not need to wait 7 days or 2 weeks to see a doctor to report, I have this, I did not feel well here, I did not feel there. The daily, the self-monitoring will give you all this information. So this is roughly the scenario and the context.
So Luke, you answered it very well, but let me just elaborate a little bit, having worked in this area. So in this case, I think dementia, cognitive health is the key, right? So question is, if you go through machine learning of the daily activities, you can get the confusion matrix. Are they getting confused, right? Are they doing sequence in a out of order, which might lead to an anomaly and maybe fire hazard? For example, they're supposed to make a cup of tea. They put the kettle on the burner without even putting water. And that could be an hazard, right? So question is, that means their cognitive ability is not matured enough or is not correct to do things. So some of these activities actually give those type of symptoms. That what anomalies do you see? Do they get confused? As he said, they go to the cupboard to bring, let's say, kettle or a cup tea bag, and they forget and they come back again, and they do that multiple trips, right? And you can observe these things, you can learn and create the confusion matrix and see the anomalies, right? That's number one. In your first question, I think was very good. So although for every person, the way you learn could be different because everybody's activity and context is so different, right? So first of all, you can give the personalized solution because you learn, but you can do the abstraction in which you are collecting these time series samples of their activities, but everybody's lifestyle has some pattern that you can learn, right? Although it is a personalized solution, you may think that, but your model is not independent for each person. You have an abstraction of the model, right? And you're learning that model, and depending on what I observe, I actually predict what you might do or how you are doing things. And for somebody else, it could be different, right? So basically, we can develop the learning and prediction-based models based on abstractions. Basically, treat these as symbols coming from as a samples, right? And the symbols, once you go through that symbol, it should be, you can do information theoretic approach, you can text processing approach, you can do mining, all sorts of different things. But you want actually personalized activity detection because everybody's activity sequence is different. Everybody's way of doing things is different, right? So it's possible. Other questions, please?
So I just located the Zoom, just try to figure out how to delete the subtitle. It's still there.
Right. So later you can see, because from my end, I tried to do a few things. I could not disable yours, and ours are not getting recorded. So I do not know exactly what it means, right? When you share the information, whether it is your stuff which is getting, but I'll also look into it later. I did not want to jeopardize the presentation, right?
Yeah, no problem. The first time this come to this problem.
I have one question before I ask that. For everybody, there are two very important talks. One on Friday at 11 o'clock. I put on the chat by a very senior person from HP Labs. He's an IEEE fellow, also a senior fellow of HP, also a chief engineer, very prolific speaker, also very nice speaker. And he's going to talk about the rise of cyber physical human systems at the crossroad of domain data and data sciences. So this Friday at 11, a different Zoom link, please attend. Next Monday, we have a speaker from AT&T Research, and that is on intelligence for cellular networks. The same time, 10 o'clock, same Zoom link. So Monday, 10 o'clock, and this Friday at 11. So please do attend. I have a question, Luke. I think you have done a lot of interesting stuff, right? It's not just one or the other, because you have the activity recognition, sleep monitoring, all sorts of different things. Do you find any common framework to deal with all of these things, or these are all point solutions in silos for each of these problems?
I think as Agile, probably at the moment, I would say data-driven approach probably still are the mainstream of the work. Probably majority of people.
But in the data-driven, do you find some common framework? Either a mathematical model or the framework that, let's say for sleep, you just tune it this way, optimize this way. For activities, I'm just trying to think whether one has to come up with different types of solutions. Although
I would think Agile, if look at the, we apply to learning style, learning and behavior, sleep behavior analysis, it's all use a different method. But I think the generic methodology does not differ significantly. But each application or its domain has its own, feature, characteristic, nature of data. So therefore, I would say the method that we do need to do to find the appropriate method suitable for that particular data type. I would say that. I'm not sure. Yeah.
Sorry to interrupt. Did you want to say something more, Lip?
No, I mean, you might have the same. Probably, I'm not sure.
Yeah,
yeah.
Yes, the point is basically this time series data may have some mathematical characteristics. The question is whether you can exploit in a data and analytic domain, and for different application like sleep versus activity versus dementia, they may have some characteristics, but in terms of analytics, but again, like we're trying to see whether some mathematical invariant can be derived or not, which will cut across different applications. That's the way we are looking at it, but it's challenging, very challenging.
But another way, I'm not suggest because we now talk about in our side, we are a little moving towards cognitive analysis.
Right.
Not just from the database to
right.
Step by step. The key we are thinking, how can we solve the interpretability
right.
problem by embedding more metadata or semantics or meaning to the either features or then we can carry on that, and then we should provide the I'm not sure a meaningful explanation when they come to a specific conclusion. So that
right.
is what we are thinking.
Any other questions? None. Did you have a question? I did not know whether you are trying to ask a question or something.
No, thank you, Dr. Chen.
Okay.
I actually don't have a question, but I like your talk. Thank you.
The talk was very good.
Mm-hmm.
Is there any other question for Dr. Chen, Professor Chen?
I think the talk is quite a high level. XC. Probably each slide, every 2 slides, there is a paper is about that. Right. So, yeah.
But the talk has been recorded. It will be made available, so people can actually go over. They can read the papers and also.
Yes, but do feel free to drop an email if you found
right.
you need more.
And usually we have a colleague actually who makes this as a YouTube version of it, and our departmental YouTube channel is MSTCS. Okay. I'm pushing actually the YouTube channel on chat. So it's very simple. All the presentations, seminars have been put on the website, so on the YouTube channel, so everybody can actually take a look, and yours will be also there eventually. So it may be by this weekend. Usually Monday's talk, we put it in the weekend time frame. So by next week, you'll be able to see your talk on the YouTube channel in our departmental link.
Okay.
Okay.
Yeah. Okay.
So Luke, thank you so much. I know it is past 5 o'clock in UK, Northern Ireland. So thank you very much for a lovely talk. It was very, I think, comprehensive, and we really appreciate that.
Okay. Thank you to giving me the opportunity to share
right.
the research.
Sure.
Yeah.
And Nan, I put a little note on the chat box for you. You might want to take a look.